Okay, let's begin. Okay, good morning, good afternoon, good evening, everyone. Welcome to the ZG Earth Data webinar. Today is our great pleasure to have Dr. Taryn Scharf speaking with us from Curtin University. So Dr. Scharf got her PhD in 2020 and then became a staff member in this year at the at the institute that she's working for. So she has been focused on the computational methods on geochronology, and today she's giving us one example of the relevant methods to predict the source rock silica from igneous zircon characteristics. So this online webinar is relatively flex. So if you have questions, feel free to put it on the chat. And later on, I could read it on your behalf, or you can directly open your mic to ask questions for our speaker today. So this talk is recorded and will be posted to advocate science. So yeah, really appreciate Dr. Scharf for agreeing to post it online. So with that, I think, Taryn, I think you go ahead for the rest of the 30, 40, 45 minutes.
Thank you very much. Right, okay, so let's have a look at predicting source rock silica from igneous zircon characteristic. Of course, this is me, and below here we have the supervisory team and also the authorship list on our most recent paper, whose title is the title of this presentation. So that's Dr. Vladimir Pizarev, Professor Chris Curtin, and Associate Professor Myla Barham from Curtin University. Before I kick off, I would also like to just take to thank people who funded this research. That's the Mineral Research Institute of Australia, Liquid Resources, and Curtin University. I myself am from the Timescales and Mineral Systems group. Right, so let's kick off. So zircon is quite an important mineral for geologists, of course. First off, it's a geochronometer. So its crystal lattice can include uranium, which decays to lead, and we can interpret the parent-daughter ratios to determine the age of that zircon. And that, of course, gives us the age of the rock that zircon is in, which is the geologic. In addition, zircon is able to capture some of the isotopic information or trace element information from the environment that it grows in, and we can interpret that information to understand something. Source of zircon. In addition, the zircon is incredibly durable, so it's able to survive through billions of years and many extreme geological environments. In fact, the oldest known terrestrial material are zircon crystals. So this makes this mineral a very useful little time capsule for us to piece together geological processes through time. This study looks at adding an additional tool to the zircon tool set, and that's looking at shape zircon, trying to get some, hopefully, quantitative information about the source of these zircon. And this raises the question, why? Where did this idea come from? Right, so let's take a step back. Let's look at the zircon, igneous zircon, growing in its magnetic environment. The conditions in the melt, the temperature, the pressure, the chemistry are all able to impact the growth of these crystals. At some point, weathering and erosion will release these crystals from the rock and they'll be released to the sedimentary environment. Transport and physical modification will happen in the sedimentary environment, but remember they are very resistant to weathering. However, it will undergo some physical modification through abrasion, breaking of the crystals, and eventually these minerals will be deposited in a sedimentary environment. And in the sedimentary environment, these zircon can be quite useful. Detrital zircon carry with them the age and the chemical signatures of their sources, and that can help us answer the questions of where the sediment was sourced from. For example, did it come from potential source A, or did it come from potential source B? Now, if we have examples of A and B, then we are able to understand the ages of A and B. and match this age information to the age information of the detrital component. But sometimes this age and potentially isotopic signature can be non-unique. For example, the ages of A and B might overlap within uncertainty, leaving us with a non-unique interpretation of the origin of these minerals. In this case, what we would like is a way to fingerprint these minerals, a way to determine uniquely where they came from in the space of spectrum. Now, what has been done in the past is a look at the shape of these minerals. These are two papers that were published prior to my most recent paper. They, of course, came similarly out of our research group because several students have been looking at this topic. And here they combine the zircon shape information with the age chemistry of those zircons to try and better determine where this minerals came from. Now, we've known empirically for a very long time that a magmatic body produces a population of zircon. And that population of zircon has physical characteristics that are similar within this population. So within a given basin setting, if I'm looking at potential sources, A and B might very well display dissimilar physical characteristics. And this allows us to compare our detrital zircon shape characteristics to those in the potential source regions and better constrain where those crystals came from. The difficulty here is that this is a comparative technique. So if we don't have material from A and we don't have material from B, if we only have our detrital zircons, can we say anything about the type of rock that zircon came from? If we suspect that the growth environment impacts the crystal development, can we tease that out? That's the question. If we can, to what extent? And this is particularly useful, for example, if we don't have the material, if the material no longer exists, what information can we tease out of that zircon crystal? Now let's stop for a moment. We talk about shape. What do I mean when I'm talking about shape? I'm talking about the 2D boundary shape of these zircon crystals. When these crystals are prepared for geochronology, they're placed inside of epoxy resin mounts. They're ground down to half grain thickness, approximately half grain thickness, as close to that as we can get. And they're frequently imaged. Here I have an example of a reflected light image and a transmitted light image of these mounts in plan view. We can take a zoom in on that and you can see these crystals. These images are frequently available, and the images can be converted into a black and white image, frequently called a binary image. And there are several softwares that can do that, and often ImageJ is used to do this. And once we have this binary image, we can easily analyze the individual particles in the image and measure them. But essentially, what we're looking at are high-level descriptors of the 2D shape of the minerals: the area, axis length, perimeter, roundness, aspect ratio, etc. And this is frequently how these have been looked at in preceding studies of grain shape. Not all of them, but it's a very accessible, cheap, and rapid imaging methodology. Now, zircon, of course, is a crystal, and crystals are actually 3D. So crystal face development is previously been looked at in terms of looking at zircon shape. Here I have an online resource that I've used for Sketchpad to demonstrate the 3D shape of zircon on the left. And to the right, I have a copy of the zircon topology scheme from Curtin 1980. So for a very long time, people have been looking at the 3D structures of zircon and trying to look at how the relative development of faces might track with certain magnetic conditions. Now, the only challenge in this, for what we're looking at, is when we're looking at these geological mounts, we're getting these 2D images, we don't necessarily have crystal face information. In fact, what I'm simply describing on this side is if I look at this reproduction of a topology scheme from Curtin 1980, Curtin Turco 1972, They show the various developments of crystal prisms and pyramids. And what I'm indicating is that various arrangements of crystal faces, very different crystal faces, can give us very similar 2D shape measurements. Here I am displaying the topology and the roundness measurements of these. And I'm suggesting that in these very easily captured images, crystal face information is not easily accessible. And this leads us to square one. Do the 2D shapes we're looking at actually systematically vary with aspects of rock chemistry? This was the first thing we looked at. How does 2D shape vary with whole rock chemistry? So to approach this question, we're based in Western Australia, and here we're very lucky to have a multi-decade geochronology data set that's been collated by the Geological Survey of Western Australia. The data set includes the whole rock chemistry of samples, and it will have the geochronology of the samples and then the images of the samples. We're specifically looking at igneous zircon and how the igneous zircon relates to the whole rock chemistry of those igneous rocks. We picked out 45 samples. We had just over 7,000 zircon crystals, and this data set spans quite a large area, age range, and whole rock silica range. Now let's start by just having a look at some very high-level patterns. What I'm showing here, I'm showing a zircon grain area, minor axis, major axis. Each gray circle is a single zircon crystal from a sample. And you can see there's a lot of spread in any given sample. But you can also see some very high-level trends tracking through the data set. Now, to draw your eye towards this, what I've done is I'm showing the median of a bin. Let's have a look here. The bin 45 to 50, 50 to 55, etc. And I'm showing how that median tracks across the data set. And these R squareds are describing this trend line. This is a descriptive trend line, and I'm not creating a predictive model in any sense here. I am illustrating high-level patterns and also the tremendous amount of scatter or variability of the shape parameters that surround that trend. Now let's take a closer look at what we see in this trend. And I'm going to propose that we're looking at, broadly speaking, 3 crystallization regimes. We have our very low silica crystallization, where we see this increase in our size parameters, our intermediate to felsic, where that gradient flattens out, and then our very high silica rocks, where we see a reversal in the size of these zones. And now we want to understand what is driving the geological processes underpinning these trends. And can we exploit that to understand anything about the rocks? We look at these eventually in the heights. So the first thing we did is we took our 45 samples. Now we know there's a lot of scatter in the data set, so we looked at the median shape parameter per sample. In this case, we're looking at the area and the roundness. Now, unfortunately, I'm not sure if you can see on your screen, and mine it's covered. Ah, there we go. Now you can see. So the area is in squares and the roundness I've illustrated with circles. And I'm having a look at the whole rock parameters that correlate with these measurements. And what we'll see is that area is tracking, of course, with silica, so the more felsic, a very high level description based on silica, the more felsic the rock, even larger the zircon area, and it negatively correlates with elements we expect to show up more mafic. Roundness, however, tracks with the solubility of the zircon. Here I'm showing M, because the M is a cation ratio, as well as calcium, which feeds into that ratio. What seems unintuitive at first is that the zirconium, the whole rock zirconium content, doesn't seem to be very strongly correlated to the area and the roundness. And in fact, it only shows up as correlated to roundness and not very strongly. So let's take a look at trying to understand what's driving these particular correlations. What do they mean? Well, we were lucky to have some billets. So these are rock offcuts related to some of the geochronology samples. And we could run phase equilibrium models for those. And a Chris Yakubchuk, co-author on this particular work, ran his mates. What we notice is in the high silica rock, our crystallization will, beg your pardon, and just by the way, if you're hearing a lot of commotion in the background, there is a departmental celebration for a lot of departmental successes. So I apologize if there's a bit of noise and cheering in the background. Right. So back to the presentation.
Actually,
yes?
it's okay. It's okay.
Is it okay? Okay,
yeah,
I can hear it quite loudly. All right.
No, there's no background noise. Actually,
Okay,
the
fantastic.
Zoom has done a pretty good job in terms of
Okay.
silencing the surrounding noise. Actually,
Fantastic.
I cannot see any noise next year. But
Okay,
it's great that you
excellent.
mentioned about that enthusiastic environment next year.
They're very enthusiastic today. Right outside the window, there's a big departmental celebration. Right. So back to the phase equilibrium models. All right. So when we looked at our high silica samples, what we see there is, firstly, whether the zirconium is partitioning into other major metals or not, is plenty of building blocks of zircon. Zircon is going to crystallize. That crystallization starts early in the rock crystallization history and proceeds all the way through to full crystallization. What we see on the lower silica end, first of all, is that this onset of crystallization is very much delayed. So there's a larger cooling period before crystallization starts. And prior to the crystallization of zircon, we have ferromagnesium minerals like our pyroxenes and amphiboles crystallizing out. We also have ilmenite crystallizing out. Now, pyroxenes, amphiboles, ilmenite are all known to actually take in quite a lot of zirconium in the rock. So remember, we did not see a very strong correlation between the zirconium whole rock content and the shapes of our zircon, but this might be because the zirconium is very much in these mafic rocks. However, it's been drawn out by the prior crystallization of minerals. Zircon crystallization starts quite late, so potentially there's quite a reduced time period for zircon crystallization, and potentially quite a reduced physical space. So what does this look like? So in addition to these phase equilibrium models, we also could get backscattered electron images and TEMA analysis of these billets. So we see in our Baltic rocks, we have these very large, elongated zircons surrounded by pulsive minerals. But in our mafic rocks, our zircon are typically quite small and found in interstitial spaces. Here, they're associated with amphibole and all pyroxene. Now, I mentioned we also had some TEMA data, and this was so that we could have a look at not only the textural information in terms of the backscattered electron images to see how the zircons are growing in conjunction with minerals, but also to quantify that. Now, the thing is, we were looking at billets. So these are zircon in situ. And it's a random cross-section through a rock, which means when we're slicing through zircon in a random orientation. So I'm not going to call the zircon sites, I'm going to call it zircon intersection length. It's not necessarily an orientated section. And our question was, do we notice that the zircon that are well developed across our various rock types, do we notice that they are in any way associated with particular minerals or particular environments? So to explain to you what we've done, we have the cumulative frequency plots. And what I've done is I've chosen inflection points in this cumulative frequency plot and said, well, these are the smallest intersections. So they're going to capture our smallest zircon as well as some intersections in larger zircon. These are our largest intersection links. They're going to capture our largest zircon. And the intermediate group will be a mix of this, although it will likely exclude the very smallest zircon. So in the next slide, when I refer to increasing zircon size, this is how we define zircon size in this context. We're interpreting it from the intersection of zircon in the billets. And what was interesting was in our lower silica rocks, we noticed, of course, that our zircon are associated with iron titanium oxides, and our iron titanium oxides have a very low percentage volume in the rock, and yet they are very important to these zircon. And in fact, the larger zircon are more strongly associated. This is a trend we see in our lower rocks, lower silica rocks. And this is what that might look like. Here you can see zircon exolving to ilmenite and adjacent to amphibole. And here it is very close to ilmenite, entirely surrounded by hematite. They also tend to be quite strongly associated. Now, what drives this association? Well, oxides, it's been proposed as they crystallize, they are excluding silica from the crystal lattice, and silica is accumulating in that crystal liquid boundary zone. And this is reducing the solubility of zircon and promoting the crystallization. This can also happen in association with ferromagnesium minerals. And this is a work that was done by Bacon. So the presence of these oxides is going to promote the crystallization of the zircon. We also know that minerals like ilmenite, pyroxenes, and amphibole, as mentioned, take in quite a lot of zirconium, and it's been observed that they can exalt zircon during subsolidus cooling. So the association of zircon with oxides and titanium using processes. Another interesting observation we had in this particular study was that the standard deviation of roundness of zircon in a sample correlates with the standard deviation in the thorium uranium values of those zircon. So when we looked at the impact of thorium and uranium on crystal size, we didn't see much of a convincing relationship, but we did notice that the standard deviation varies. This suggests that there is an extrinsic process which might be linked to the variability of the zircon roundness as well as the variability of thorium-uranium ratios. The thorium-uranium crystallization of these. So we're looking for the fractionation of these minerals in the melt. And we've seen some work on maybe cumulates that illustrated that although you might not expect zircon to form, they do because they can grow in interstitial spaces where you have these disequilibrium conditions where the materials are available for zircon growth. So looking at this all together, we have our three paradigms of crystallization. We're proposing in our lower silica rocks, we're seeing these smaller, rounded zircon. They're crystallizing out late. They potentially have less time to crystallize out. They have less space to crystallize out. They are disequilibrium. They reflect disequilibrium processes. They might be highly dependent on the presence of iron titanium oxides, amphiboles, pyroxenes, either for scavenging zirconium from these minerals or for their ability to promote crystallization of zircon. In the intermediate to felsic environment, we have a material freely available for the growth of zircon. We have early onset of crystallization, potentially long crystallization periods. We're not physically constrained. One thing we did notice is that the high silica paradigm, we again see smaller zircon, and now we didn't have ability to investigate in this context. What we are suggesting is, from the literature, we've noticed that in high silica, the presence of water has been seen to delay the onset of zircon crystallization. So again, we might have this repeated occurrence of zircon in these physically constrained spaces, and of course, slightly lower whole rock zircon in these rocks. Right. So then we thought, okay, so if we see this trend line, and we suggest that there are actual heterogeneity controls in trend lines, is there anything predictive to them? Well, the short answer is no, they're not predictive. We had a look at, if we have the whole rock silica, what is the trend with the area or trend to roundness? Now you can see there's a trend line. You can see there's an awful lot of scatter around this trend line. It is not predictive. It is a very interesting descriptive model, and it does reflect quite a substantial percentage of the variability of the data set. When we look at trying to predict the silica of the rock using the roundness of the area, again, we see that this perhaps accounts for about a quarter of the variability of the silica in our data set, but it's not predictive. But it's an interesting trend line. And this led us to the question of, this led us to the question of, can we get a predictive model? Because it seems that the 2D shape that we get when we image these billets is a reflection of extrinsic controls of the zircon, and that our source chemistry might predispose our shape population, and that there are at least significant relationships population level, but shape alone is not enough to actually tease that out. For anyone who's interested in this, GQ. So how do we get to a predictive model? So we went back to our data set. Again, Western Australia. Again, we're focusing on igneous zircon to whole rock because we want to see if this relationship exists in the starting point. We slightly reworked our data set and expanded it a bit. We also added the zircon, uranium, and thorium content and zircon internal texture. Now, these are parameters that typically be available if one were conducting a data set. But the question is, if we have this data, can we extract quantitative information to use as an additional discriminator in these provenance studies where we typically look at search? Right, so this is the trend through the data set. Again, we've had a look at this. We have seen these polynomial trend lines, and we notice that they will inverted high silica. This is the work I mentioned. So in this particular study, we were using neural networks, and you will see in a moment that this shape inversion at high silica became a bit of a confounding factor. Another hurdle we had to overcome is that we have less data in the intermediate silica range than we did in the felsic and in the mafic silica range. So we wanted to get a balanced data set for the silica range, and also we wanted to have as much data. Now, in training neural networks, we want to have very large data sets, and sometimes it's not physically feasible to create large enough data sets. Now, your model is only as good as the input data, so hopefully you have a fairly good slice of data to start off with. And from that, we augment the data set to create modeled data based on data. In our particular case, what we did is we went sample by sample, and we created zircon aggregates. So I would merge two zircons together within a sample, strictly within a sample, merge the shape parameters to create a modeled zircon value. And in doing this, we augmented the amount of data and also balanced the data spectrum. CL texture. Now, cathodoluminescence texture has been around well, and folks have used this to interpret aspects of origin and history, but it's interpreted visually. And in this case, what we've done is we've just coded for the presence or absence of these textures. If we limited texture, homogeneous vectors, and this was coded at the sample level. So a sample can have multiple of the texture parameters available. The next thing we wanted to do was have a look at the neural network and how to design the neural networks. We had an array of data, and we wanted to understand which data was most informative to the predictive process. So we had to test various input data scenarios. Not only that, but for those that are using uranium and thorium, our data set is actually limited to a subset of the data that measures, so it's gray. Whereas if we're only looking at photoluminescence shape, we could use the full data set. So what we'll notice in our test is we not only test for input data set, but we also test against subsets. So that, for example, the shape of CL input scenarios can be comparable to the shape of thorium input scenarios. So for each of these input scenarios, we need to design a neural network. We used our tuner to guide the design process. Now, tuner is a hyperparameter optimization framework. We use it to guide layers, dropout, nodes on various layers. To test the performance on each optimized model in the end, we would run that on our test data set. We used a 9-1 split of our data. So before we did anything to our data, before we augmented it, we took off 10% of those rates. Those are what we will use as a test data set to compare performance. We also use a 10-fold cross-validation. So cross-validation, when your training data set will be subset into 10 different subsets, you will train on 9 of them and validate one of them, and we'll repeat this 10 times, iterate the training data set. And what I'm testing for here is I want to see stability in the performance of the model. Now, you've often probably heard that people speak about neural networks as proxies, but there are tools available to quantify the feature importance, in other words, the importance of the various input parameters. In our particular case, we used Scharf. Right, so this table comes straight out of the paper. Let's take a closer look. The very first thing we noticed, dataset A1 simply refers to analyze zircon only. The very first thing we notice is if we constrain the silica range, we get a much better performance. Now, my interpretation of this is you would have seen at least in the shape graph, that the shape parameters are very high silica, similar to those at very low silica. You'll also notice there further on in the next few slides, there are similarities in CL textures. So I think with the data we've used and the way we've used it is just at this higher silica range, it is not distinct from the low silica zircon. So performance drops. Now, we're only looking at a limited silica range. That's it's not inherently a bad thing, because I would expect that zircon in the very high silica rocks are more likely to be inherited zircon. The next thing we looked at is the shape alone and what we find. And the comparison here that we're looking at is a comparison between analyzed zircon only and all zircon. So just simply a difference in size. We don't really improve our performance we see on regression, that the original did. Including our cathodoluminescence texture does give us that great improvement in performance. Uranium and thorium, only a very slight improvement in performance. And our model that we went with, that we thought was the best model, was using all these parameters together. And that's what the shape, CL, uranium. Let's have a look at what that looks like on the test data set. What you're looking at here, the individual white dots are individual zircon ethers. So you will see there is some smearing along this idealized 1-to-1 correlation. But that's an awful lot improved from what we had in the regression analysis. The other thing we noticed was that some of the zircon was coming from the top, and the bar graphs are grouping the zircon according to individual samples. So when I've got multiple zircon, the median of that, now in this case, a very small test subset, so not many zircon looks from the test set, but the median typically lies within 5% of the measured silica value. Using Scharf, we had a look at what was important for these estimates, and we see the presence of sector and homogeneous donation. When we consider the presence or absence of CL textures on the data set, that these textures are most prevalent in the lower silica. So this might be helping our model indicate that portion of our data set. The next most important features were what came called principal components 3 and 1. Now, we didn't throw all our shape parameters in directly. We ran it into principal component analysis. Principal component 1 is largely informed by shape parameters that comprise the zircon. Principal component 2 is largely. But this is now trained on a Western Australian data set and tested on a Western Australian. What happens if we look at a completely unrelated data set? So we used some meta from Greenland. We used the zircon that we interpreted origin. And we ran the estimate on these zircon. And these are what the results look like. Again, we will see a big scatter, which is very reminiscent of a very broad scatter we see zircon shapes from any given rock. But again, what we notice is the median from these estimates is increasing order of is predicted. I would like to point out that we did this week actually some taking break test. Now, this implies that if you wanted to use this technique, you'd have to run it in zircon population. How big a population would you need? So we looked at our zircon grains, and we went through these samples, starting at one zircon, incrementally increasing to the factor zircon. And we would select, for example, if it's 3 zircons, we randomly select 3 zircons and we repeat that 100 times. And then we had a look at when the error tapers off and when the variance in the error tapers off. After about 10 zircon in a population, have error to 5% or less, and minimize our variance. And obviously, the amount of error is very much dependent on the original variability. So now, this was our first take at looking at a predictive link between zircon characteristics. It's important to note that these are based on population traits. So there's a tremendous amount of scatter in these estimates. So I wouldn't suggest looking at an individual zircon to get a zircon, but if you had a group, and ideally more than 10, you can get to say something about it. In our case, the medians were typically less than 5% silica. Now, we were looking in these investigations in igneous rocks, so we of course knew which zircon was part of the population. But ideally, where we'd like to progress to is to be able to use this in a detrital setting. But this implies we need to know which zircon is part of the population, so you would need additional information to assign it. This work was published. Anyone wants to get involved? Right. Thank you very much for your attention. Any questions? I'd like to hear about them, and if anyone would like to reach out.
Okay, it's great. Thank you very much. Now it's time for questions from our participants. So feel free to open your mic to ask a question or post a question in the chat, and I could read the question on your behalf. So please go ahead.
Yeah, thank you.
Okay, let me start from one question. Well, others might be doing more questions later on. So I have a question that I think this is really cool. And do you think that what are you working on this kind of, like, say, for example, could create an app or a place where people could upload a zircon image and call it AI zircon, something like that? And then
So yeah, go ahead. Complete,
yeah. Because although technically it is possible to do, like, say, from image and then convolution neural network or even transformer directly from image to get the results, but I think your way of training it could be much better in terms of computationally effective, because we don't have to waste so much computational power to basically analyze pixel by pixel. But in your case, that basically simplify an image into the different features, and then later on work on those features, also this Tableau data, to either go to neural network or other machine learning algorithms, and then achieve the goal. So, but I think from the user end, it will be more intuitive that if people just upload a figure or image, similar like AI photo, right? So upload the photo image, and then they could tell you the result. I think by that, they could also use another way that could accumulate a large amount of zircon image data in the world. I think that could be soon could
absolutely. Well, assuming that folks are happy to allow us to use that data. So I am pleased to hear you ask that question, because it tells me that people might be interested in an app like that. So the story of my PhD, the first paper out of my PhD, I was trying to have a look at a means to analyze zircon, and I wrote an app in Python which we called Analyzer. And Analyzer, I am sure, might be, I wouldn't say it's the best user experience, but it was a first step. And what we subsequently did is we've had the great fortune to engage with some students that come from programming background and develop a web that can take these grains and take the images and execute this. And we have an improved user experience, and we're working on improved extraction of shape parameters. We haven't put it live yet because we're busy bug testing it. But yes, there actually is something. And hopefully we will have that out relatively soon for people to look at and try back on and see if that's something that's useful to you.
Okay, thank you. Questions from our participants today? I have another quick question. That I think in your paper you mentioned about neural network, but have you tried other machine learning algorithms, like common ones, like XGBoost, etc., that probably could achieve the same goal? I don't know.
Yes, absolutely. And I think that's a very important point. In this case, and I guess it has to do with the history of these projects. Well, we were using neural networks in our original take on the data. We had a more complex data set. In the end, it was simplified quite a bit. And you'll notice, as particularly if you have a look at the results table, the model we ended up using was only 2 layers. I absolutely think that you could achieve some of the results using simplified parameters and simplified models, simplified techniques, because the inputs, at least in this study, are quite simple itself. So if I were to reconstruct the study, having all my learnings from it, absolutely, I would try something like
that. Okay, I actually have another following question.
Sure.
Because I think you provide an excellent example of how we could use a geological sample's morphology to infer, in this case, chemistry, and probably I believe people in the community who are working on zircon, whether I don't, to indicate, for example, erosion history, etc. But I think if we would zoom outside, I think there are different communities that are working on different morphologies. I mean, for fossils, as well as for aerosols, etc. So I don't know, for this morphology perspective of this geological samples, is there coherent, like say, platform or packages?
In terms of how people are measuring the morphology? Yes, so definitely. Have I understood you correctly? Yeah.
Yeah.
So
Yeah. That's part of it. I mean, another way is that is there any universal, let's say, tool or packages to deal with all morphology related, let's say, image analysis? Because it looks like to me that okay, for zircon, people do it from scratch, and then next time people do a diamond, people do this from scratch. And next time people do quartz, and people have to do from scratch. And then we have 4,000 minerals so far we know in the earth. So basically, that's a little bit slow. I don't know. Is there any
way that
accelerate?
That's an absolutely interesting point, and I think like all science, the approach to things and the take on things is continually evolving. So you've hit upon an important point. First of all, different techniques could also calculate shape Now, what's very common that I've seen is the use of ImageJ. Now, ImageJ was designed for medical purposes, but it can do quite a lot of image processing, and that gave these high-level parameters. And quite a lot of people have used that, and that's why I went with these high-level parameters as well. I myself didn't use ImageJ. I made Analyzer. Analyzer shape parameters are quite comparable to those output in ImageJ, but it allowed me to do some extra data wrapping, connecting data to uranium, thorium, etc. There's obviously the question of whether you want to do 3D shape analysis. There are softwares out there that get linked to machinery that does 3D analysis, which is a whole different ballgame. We were focusing on 2D parameters because it's quick, and also if you're looking at historical data, there's quite a lot of that, and we were interested in how we could develop this. There's quite a lot of data available, historical, that we could tap into, and frequently people do high-level 2D analysis, so can we get something a little bit quantitative to that? So ImageJ is used a lot. However, it has also been raised that these shape parameters might not be they were designed for biological processes. It might not be entirely well fit for geological processes. So I have seen some work done 4 years ago looking at trying to get more geological shape parameters. This was designed for use in MATLAB, however. So I am not aware of how spread the use of that is, but it has been acknowledged that these high-level shape parameters might not be entirely suited to geoscience. So to answer your question, what I've seen mostly is the use of ImageJ, but also the geological community has noticed that the best shape parameters to look at 2D objects, and there might be additional shape parameters you want to look at. And some people look at 3D shape parameters, or use software that take a 3D mounted zircon, get a projection of that. It will produce similar shape parameters to what we get from image shape. That's quite a different technique. So there's no universal consensus, but I also think what you use is dependent on what you're trying to achieve in science. People will vary their methodologies. So there's no one answer, but there are some software like ImageJ.
Okay, yeah, thank you for answer. And next question is from a participant, Dong Hao Zheng from Princeton University. And he said that Dr. Scharf, very impressive talk. I wonder if there is an orientation dependence of your model based on the 2D image. Many geological processes seem to enforce zircon to have a preferred orientation, which may influence the apparent shape of the zircon in 2D image. Will this affect the model? I think your 3D model will address that, but I don't know in your 2D model how you comment on the orientation problem.
No, absolutely. So what we had looked at were zircon separate. So our zircon had been released from the rock and placed into zircon mounds. Now, a few factors come into play here. Now, zircon typically can have an elongated form factor. So these zircons are placed in mounds and they will typically lie along the long axis. So they are, I'm going to use the phrase pseudo-orientated. So allow us to see the 2D slides through the zircon. So to clarify, the zircon we looked at, we're not in the rock. So the orientation in the rock isn't what's going to impact it. We looked at them in mounts. Now, they are expected to have a preferential orientation in mounts, given the form factor that the zircon typically grows in, but this will also be affecting all mounts simultaneously. If the question applies to when the zircon is growing, that is a very interesting question altogether. That I haven't looked into and I can't comment on that. But if the concern is orientation of zircon in the mount, first of all, they're removed out of their rock and they're will tend to have aligned along the long axis. So the prominent shape parameters that we'll be analyzing are reflective of the cross-section.
Okay, thank you. I think I have one last question. I think that then we can finish. So I think you are more affiliated with industry than I do. So
Oh.
I know that from your perspective, but talking in general sense, don't have to tell any specific details because that might have conflict of interest with commercial use. So do you see that how does this images play a role in, for example, the mineral exploration or
Yes.
the process? I bet the industry mining industry are very interested in that because that the image is more available than the geochemical analysis that's currently available. So, but yeah,
Well,
I don't know. I don't know. I think you know it much better than I do. So could you share
well,
something about that? But don't have to tell anything that has a commercial conflicts.
sure. So my particular PhD research formed part of a larger project that was investigating zircon and whether anything of use could be useful to, whether any data bigger could be of use to, you know, understanding certain mineral paradigms. Now it's very early stages. I would say that it's interesting to have a look at the images, but we're looking at silica. So silica could be used as an additional discriminator when I'm trying to understanding the source of your zircon. That has used, for example, I in the beginning of this talk showed a title of a paper came where one of our students was looking at a basin, a sedimentary basin, hosts heavy mineral sands, understanding the origin of these minerals, the history of these deposits, and how this information helped them better cover coming from. So at this point, these direct applications would help with provenance analysis. Provenance analysis can be useful in understanding the geological system. I think quite a lot of work would still need to be done to extract information, to see whether it's even possible to extract information that has more direct application to exploration processes. And also that information would vary very much dependent on the commodity that is being looked at, mineral that's being looked at as well. So right now, let's say it's an interesting concept in provenance analysis. It does absolutely raise the question you just put forward, can this be used in exploration? And my answer to that is we would need to look to see.
Okay, great. Thank you very much for all this interaction. I think it's very insightful. And okay, thank you again, Taryn, for giving the wonderful talk, as well as the time that's spent in preparing everything. And this video will be posted online, and I believe there are a lot of people are going to click the videos because it is accessible. I bet it is a very good talk that had a broad interest in the community. So with that, let's sum it up, and thanks everyone for your participation today, and thanks our speaker today. I'm looking forward to seeing you in person again in the future. Probably pass each other
Thank
in
you so
person
much.
2 weeks ago.
Thank you so much for having me.
Okay, see you, Taryn. Bye-bye.
Have a lovely day. Bye.